They'll both do it. Wait till you take genetics. Well, you could always switch to one of the physical sciences. We could just do math. I could take you through physical chemistry. We will learn fermionic quantum mechanics. Yeah. Yeah. I also got a shirt that should finally convince my students to stop asking me biology questions. Because they don't know the answer. People go, what does this mean? I'm like, I don't know. I'm the professor who walks around the building going, I reject human, wish to return to monkey. And someone gets like, I swear to you, a student will, that's not how it works. I don't care. We have this one. So yeah, I'm tired of people asking me biology questions. Uh, I, I'll give you answers. I dare you to use them. That's my rule. I will give you answers. That's like it's like my rule. If I'm at a coffee shop and a parent leaves their child unattended, I will give it caffeine. Oh, I'll always come up with an answer. It's probably not the right one. All righty, gas laws. Because these are leading up to which equation? What are these all leading up to? Yeah, the ideal gas law. You already sound bored. You already sound bored. Can you put like a little happy in that voice? Because you're sitting there like picking your hair on the ideal gas law. You're just so overjoyed to get your education. I don't know if we have an experiment on that. Now, the experiment you're doing the formal lab report on is a titration. So I don't know if you guys liked titrations last semester or you were bad at them. Yeah. You have to titrate the antacid until you neutralize the base in it. All right. Oh yeah, because you can turn it like fluorescent pink. It's amazing. But you like when you do that, you're gonna want to add like some really pure base. Like I would get like 6 molars sodium hydroxide and put it in there. It'll turn super pink. Just don't be. I saw a student one time go, "What'll happen if I do this?" She put a drop of it in the bottle that had the sodium. She goes, "Well, what?" She goes, "Well, what does it hurt?" I'm like, "You have to remake the whole thing." Goes, oops, yeah, oops. So don't do that. Okay, so we have 3 main gas laws that we're going to be learning. Boyle's law. Remember, constant temperature. That's the key to this. At constant temperature, every single combination of pressure and volume equals the same constant. Remember that? Yeah. Remember that constant is going to end up being the slope of this line because if we rearrange this, yes. Yeah, this is like my whiteboard. I don't know.
Yeah, but it's not a, maybe, like,
What are you talking about?
it looked like you were, it looked like you.
Yeah, yeah. As I'm writing on here, that these are the notes. So it's just like I'm writing up here. So yeah, you're supposed to see it.
Yeah.
You trying to tell me you're a stream sniper?
I,
I'm learning new words. I'm old. I didn't know these words until someone said, "Oh, we have stream snipers." I go, "What the hell is that?" Apparently, when you play an online game, it's someone who watches your stream to find out where you are and what you're doing so they can come and kill you. Mm-hmm. Yeah, yeah, when you play with the screen and like the 4s and you're watching someone, they go, "Stop watching my screen." Same idea. So remember that this equals our y equals mx plus b equation, where the y-intercept is going to be 0. And then we brought in a new mathematical symbol, v. Efficient. It is a logic symbol. It will make you learn the whole library. Okay, so what does that symbol mean? What do we say it meant? Proportional to it. But since it's also v is proportional to 1 over p, how else can we say that? Yeah. So if we have one is proportional to 1 over the other one, so it's like v is inversely proportional to p, vice versa. So you could also say inversely proportional. It's just stuff you'll see written somewhere, and I kind of want you to have an understanding of what the language is saying to you. And of course, the way you turn a proportionality symbol into an equal sign is with a proportionality constant. You have to take the proportionality multiplied by a constant, you get it, then you have the two things equal each other. The thing is, you don't know what that constant is, then you have to do science and figure it out. Now, because every instance of PV equals this constant, I can therefore start setting all the PVs equal to each other, and you've probably seen this one before. Each one of those equals the same constant, so they all equal each other. So this is where you get your Boyle's law of P1 V1 equals P2 V2. And again, if you're working a problem, you can only use this when, what's the key? Constant temperature. All right, so let's work through a quick exercise. Aerosol can contains, now I want you to pay attention to this. Let's talk about significant figures. Who really enjoyed doing those last semester? That's about as many hands as I should see. So, okay, I don't really grade sig figs. There are places it matters. So like if I had you in 500 level nuclear physics and we were looking at reactor physics, yeah, I'd grade you on significant figures because an error of like 0.0000001 is the difference between a reactor that works and one that goes thermonuclear and destroys everything around it. So sometimes it matters. Significant figures also super important because you don't want to eyeball. So, but in here, I'm not really so much worried about your sig figs. I'm more worried about your logical process. So as long as you're close, I'm not going to grade it. Now, if you're the kind of person who likes to, have some fun, and you multiply a number of 4 sig figs by a number of 3 sig figs, and you give me a number of 28 sig figs, I'm going to catch that. I will laugh, and I will mark it wrong. So, as long as you're close, I'm not going to pay attention to them. But I also wanted to know if you had seen this last semester. Look at that 400 milliliters. Does that look different? Exactly. If you see that decimal point there, it doesn't have to be anything after it. The way sig figs work, 400 on its own would be ambiguous. So 400, that could be 1 sig fig or 2. It's ambiguous. If you put that decimal point on there, it forces it into 3 sig figs automatically. So that's what you'll see that in the book. That's what they're doing. They're saying this is a number with 3 significant figures. Okay. Okay, so aerosol can contains 400 milliliters of compressed gas at 5.2 atmosphere. And all the gas is sprayed into a large plastic bag. I still think that's funny. I mistyped bag. Apparently now we're spraying gas into a bag. Speaking of which, be careful letting Russ give you random facts because ruin you there. He's telling me how the giant windmills kill bats. Because he says the pressure differential in the air behind the windmill is so great, and since the mammals, their lungs can't adjust, it literally deflates them and they drop dead. It's like, awesome, man. I'm gonna go back 20 hours to be depressed now. That's great. So, but that's supposed to say bag. You spray the gas into the bag inflates to volume 2.14 liters. What is the pressure of the gas? I said that twice. Why did I do that? Coffee was wearing off. Okay, so assume constant temperature. So now we know we can use Boyle's law. Okay, so what we're going to start with, it's not as bad as a professor we used to have here who would give me random facts. And I was like, dude, like I can't drink tap water anymore. Can't. Do what? Yeah, you don't want to know. Trust me. Let's just say it has something to do with our government going, good enough. Our EPA is not exactly a hardcore PA. They're more of a good enough institution. So, what are we solving for here? The second pressure. Now, here's the thing. You could call it's going to come out the same. If you want to call the bag that you're spraying into pressure one, I don't know why you would. Maybe you're a bag supremacist. But as long as you solve it correctly, you're still going to get the same number. So that's what we're solving for. Now, and I said this last class, I never mean anything to be demeaning. I say things that I think are funny, and some people are like, "Are you calling us dumb?" No, it's not. But this question, we have to change something, and it's my favorite Sesame Street game called "One of These Things Is Not Like the Other." It's like I was hanging out with someone one night, and they go, "On TV, who like of all the TV vampires, who is your favorite?" I said, "The guy on Sesame Street," and they said, "He doesn't count." And I said, "I assure you, he does." But, he does literally count. So what do I have to change though? Yep, to match the 2.14 liters. Look, I can't do math if my units don't match. So you have to make sure you're doing that. Now, I don't care if you just move the decimal place, but I want to just make sure you know the conversion. How many like, how am I going to convert this? What's the conversion factor? Yeah, how do we do that? Where does the 1,000 go? On the bottom. You can say, well, I'm trying to cancel out milliliters, so I'm going to put it down there. So now all the units match. So I'm going to start plugging things in. So our P1, our our V1 is going to be 400 milliliters over 2.14 liters. We should get something about 0.972 atmospheres. Now, when you're doing assignments, if the problem doesn't specifically tell you what unit to solve for, go ahead and just use the ones that are there. Okay. Like if you're doing something and you come out with milliliters, you're like, should I put that in liters? If the problem doesn't tell you to, just leave it the way it is. I really, really try not to play guessing games. Like I don't put something on there and go, how dare you not know what I was thinking? I did get kicked out of a class when I was an undergrad because I told my professor, I'm sorry, my crystal ball's broken. I couldn't read your mind. I've learned how to control my outside thoughts a little more as I've grown up. So our next law is Charles's law. Well, look, we have another condition. Constant pressure is necessary for this. Charles's law, volume is proportional to temperature. Now, to get an equal sign, we need a proportionality constant. And then once we start looking at this, this constant is going to equal every instance of volume divided by temperature. So we can start doing this. V1 over T1 equals V2 over T2. And I will tell you a fun video to watch. You've seen people on helium, right? You hear what happens to their voices. Have you ever seen the videos of people on sulfur hexafluoride? Oh, yeah. It's amazing. Sulfur hexafluoride will turn Claire into Arnold Schwarzenegger. It is, it just, you don't believe it until you see the video. It's just unreal. So now, the second way we work through problems in this class is now you're going to spend some time working together, a couple minutes, 2, 3 minutes working together to see if you can figure this out. And then we'll go through it. So some of these I'm going to give you a little time to work on them and think about them, and then we'll go through it. I can't force you to work in groups, but you want, I suggest it. Before I got this job, I had 2 jobs. I had to choose between that and also from this place, and also from the Army Corps of Engineers. They were working on something really cool. They were working on the next generation of uniforms. They aren't sewn running. So instead of polyester fiber, they're grown, but in the fiber, they manually manufacture the uniform itself self-fit. Yep, no more heavy caps. You know, if you go look at the best outlets, but they were using like nano technology to grow the fiber to the uniform. I'm described for this. So I got that off. I didn't know if it wasn't working. The guy from my graduate lab left the post, he did a post office, but he left there. And he now does software programming for, he like programming software for keyboard machine. There was also a company in Chicago called Lumac, and inside the uniform material, they put these crystals as perovskites. And what those crystals did was they had little chambers in them that actually captured themselves for biological and chemical. So what they would say to the uniform. Now, once you use the perovskite that you use up, you get a uniform, but they would keep 99% of all biological and chemical. I would say you guys are right on it. Also, if I ask questions in class, please don't mumble. Remember, I'm old, and when I was your age, I worked security at rock concerts. I can't make out mumbles. Yeah, I was with the company I worked for, I was an insurance person's dream because I'm big enough to make people think twice and I'm very non-aggressive. So you look confident. You look sad. I'm not sure if you got the right answer.
Um, like to zero and yeah, afterwards, so like.
You know,
No, so she's.
that could be an issue. That's a whole order of magnitude different, but you know, does everyone have an answer for this? Well, of course, we're in that section, so we're going to be using Charles's law. So like when you're doing assignments and stuff, I do like you to start with the theorem and solve for what you're looking for. Because here's the thing, like if I'm correcting your logical process, you could even be starting with the wrong theorem. I need to know that. You may be doing it a different way, but you're starting with the correct theorem. And I kind of want to get a beat on how you're thinking because you're doing it fine. I just want to make sure I'm able to track it. Now, what did we solve for in this case? Mm-hmm. So here we'd start plugging numbers in. Now there is one we have to change. What is it? Right. How do we do that? Yeah, for this class, let's just use 273 to keep it nice and simple. When you come to physics, I make you do the 273.15. So we need Kelvin. Okay, so what we're going to have here from the volume we get should be about 239 milliliters. So who had too many zeros or not enough zeros?
I did mine in this, so I got the same answer, but it's in this.
Ah, well, then you're okay. All righty. I'm sure you guys remember this dude. You loved him, Avogadro. Not only was he the master of moles, but he also played with gas. Avogadro's law. Volume is proportional to the value n. What is n? Moles, number of moles. So again, we have the proportionality. So proportionality constant. So every factor of volume over number of moles is going to equal the same constant. So we can start using the V1 over N1, V2 over N2. No, that's not what we'll use that later. Right now, we're just worried about using this law. Okay. And what has to be, so the main key here, same temp, same pressure. Okay. That's just a proportionality constant. So let's look at this one. We're solving this one with an actual chemical equation. So the one on the left is called nitrogen dioxide. How would you name the chemical on the right? Is it a covalent or an ionic compound? Covalent. Because remember, compounds made up of nonmetals are covalent. Compounds made up of metals, nonmetals are ionic. Yeah. So how do you name a covalent compound? Two N's is what? Nitrogen, about 4 oxygens. Yep. Dinitrogen tetroxide. You only use those numerical coefficients for covalent compounds. Well, let's see, 25 milliliters of NO2 gas completely converts to N2O4 under the same conditions. What volume will the N2O4 occupy? Okay, well, we can use Avogadro's law. We're solving for V2. V1 N2 over N1. Now the question. The volume's easy. What about those numbers of moles? You're one of those smart people that makes things very hard.
I mean, like, you have to put it into like. convert-
A lot of times you do. A lot of times you do. In this case, you don't. In this case, here's a word I wonder if you heard last semester. You're using the stoichiometric coefficients, which are what? Coefficient. 2 moles to how many moles? 1, 2 to 1. So your N2 is 1 mole. Your N1 is 2 moles. So a lot of times, yeah, you do have to do those calculations, but sometimes don't make it harder than it has to be. So when you calculate this, you're going to get 12.5 milliliters. So when you're looking at chemical equations, remember those coefficients are always moles to moles. And the vocabulary word for that you'll see in so many books is stoichiometric coefficients. So a little practice here. Here's a nice question that you might see on a standardized exam. Work together, see if you can figure out what the answer is. Yeah, you guys locked in fast. You ever think about changing the class into who wants to get an A? We'll just do like 50 points and we'll just sit there and get like 4 choices and you'll have to say like, final answer. Like, are you sure? Because if that's your final answer and it's wrong, you get a D for the semester. It just, yeah, a heck of an easy way to grade. I just ask questions and if you get them, great. If you don't, well, better luck next time. Okay, what do we think it is? It is B. Well, we're not playing yet. And trust me, if we were playing that game, maybe a little harder. I would get used to questions like this though, because these are like things you'll see on standardized exams. These are like questions like this is what you'll see on your tests in here. So make sure you can read questions like this, parse them, and answer them. Now we're up to the ideal gas law. And this is the law that's always super awkward now because of my class, my first year here. So I had this up on the board, PV equals nRT. There's a young lady in class just completely zoned out, just gone. And I bring this slide up. About that time, she zones back in. She has no idea what we've been talking about, but she looks at the slide. She goes, "Who's a pervert?" And I said, "That is not what that's not what that says." You know, I would try not to zone out in class. So let's look at some of the laws that we've had. Well, we've had Boyle's law. V is proportional to 1 over P. Charles's law. V is proportional to T. Avogadro's law. V is proportional to the number of moles. So when we put this all together, we say that V is proportional to NT over P. And we need a proportionality constant. B equals, and that constant we know is going to be R. And that ends up leading to the PV equals nRT. Now, this is the logic argument on how this works. If anyone wants, we'll bring in the full statistical mechanics derivation of how to get here. But that usually makes people quit the class.
So are there going to be different R's because there's different types of materials?
Yes. They're not pressures. But so this R value here, this is the one you're going to use for your gas calculations. We're going to get to a point where you're going to have to use R in terms of to solve energy problems. So there's a second R you're going to learn that has joules in it. But that's what you're looking for. If you see the energy unit joules in the R, use the other one. There is, but we're just going to, for all of our calculations, we're going to use this one and translate things into like atmospheres. So yeah, you can Google R. There's a bunch of them. But I want you learning how to use this one and translate your units to match this. Now, this problem I pulled from the textbook. I was typing it, didn't quite see what it said, and then all of a sudden went, wait. Okay, so imagine we're in lab here and your lab partner accidentally swallows a drop of liquid oxygen. Okay. If that happens, this is why we need to start taking warning labels off of things and let Darwin and its course. First off, I'm never going to give you guys liquid oxygen. You ever watching the videos of the rockets that went to the moon and you see all that like stuff falling off the sides of the rocket? That's ice. Because inside that rocket is liquid oxygen or rocket fuel. And the reason, first off, you're not going to accidentally drop some in your mouth. And I'm not going to give you any in lab because it's freaking cryogenic. So but fine, the textbook wants to ask about somebody accidentally swallows a drop of liquid oxygen. They had to have like security clearance just to get it in the first place. All right, fine, I solved that problem, I guess. So sometimes you read the problems in the book, you go, there's no way that's a realistic scenario. There's no way. But that's what they wanted us to do. So I'm like, all righty. Trust me, you wouldn't, it's not, again, it wouldn't be one of those things where you go, whoops. You would know. You would know because it would hurt like you've never hurt before. You ever swallowed anything at negative 400 Fahrenheit? Yeah, I don't think so. So fine, book, we'll just do it that way. So let's see. The oxygen has a density of 1.149 grams per milliliter. The drop has a volume of 0.050 milliliters. What volume of gas will be produced in the person's stomach at body temperature and a pressure of 1 atmosphere? Okie dokie. So we're going to end up using PV equals nRT. We want to solve for the volume of the gas. We have to figure out how to do that. So first off, we know that our R value uses Kelvin as its temperature. So the first thing we want to do we want this in Kelvin because we want to make everything match our constant. Okay. Now oh shoot, that doesn't look right, does it? Okay, there we go. So we're trying to find V. We know R, we know T, we know P, we don't know N. How are we going to find it? We do. Mm-hmm. Yeah, so the process we're going to use is we're going to go from volume to grams to moles. Okay. So what do we start with? We start with 0.05 milliliters of O2. Okay, so then I'm going to say, well, I want to get rid of milliliters, so I can do that with the density. Now from here, I want moles, but it's O2, so what do I have to use? 32. And in these conversions, when you're using molar mass, always put the number with the grams, okay? So whether you're going to put the grams in the bottom or the top, the number always goes with grams. Because you notice, just like we said, milliliters, let's see. Nope, see that, I should have put milliliters there. Milliliters divides out, grams of O2 divides out, we end up with moles, okay? No, so that's the molar mass. So O2 is 32 grams per mole. So what we get, now we have our value of N. So now I'll say V we'll put in our moles. Put in our constant. Our temperature over our pressure. When you calculate this, V is going to equal And what will the unit be? Liters. When you're doing these, again, since it didn't explicitly say it, you can leave it in liters. I don't care if you feel more comfortable putting 45.8 milliliters. It doesn't bother me. You just kind of want to look at your units here and say, well, moles cancels out moles, Kelvin, Kelvin, atmospheres, atmospheres. I'm left with liters. But did everyone understand how, like, would you be able to look at this and say, well, I have a certain volume of my oxygen, I have a density, and I want moles. Would you be able to look at that and parse out what you needed to do? So make sure you practice stuff like that, seeing what you have and figure out how can I get from here to where I need to be. That's why one of the things I write out the theorem first. I'm like, okay, if I look at this, I'm trying to calculate V. I have R, T, and P. I must be N in some way. What do I have that can give me that? All righty. We will be back on Friday, and then sadly, the school thinks you already need a day off, so I guess no Monday.